All right, this is section 2.2. We're going to be working on slightly graphing some polynomial functions, but more importantly is studying the behaviors of the graphs, some of their characteristics. Our polynomial functions are going to be polynomials that have higher exponents like x to the third, x to the fourth, fifth. Characteristics of the graphs of the polynomial function. Polynomial functions are continuous. This meaning that the graphs of polynomial functions have no breaks or holes or gaps. This is an example of a polynomial function just by looking at it so that you know it's continuous. It goes on forever and domain would be all reals. So that's a continuous graph. The graph of a polynomial function have only nice smooth curves and bends. There are no sharp turns, such as the y equals absolute value of x. No step functions, no piecewise. We're dealing with curve functions. Linear equations are considered to be polynomial functions. Quadratics, cubics, quartics, those are all examples of polynomial functions. We will first look at a simple polynomial function, f of x equals x to the nth power. We can break these two cases, n is even or n is odd. So when we have this function, you might have f of x equals x2 where your exponent or the degree is even. And so if it's even, there's some specific characteristics about it. We are also going to look at when n is odd, x to the third or x to the fifth or any other odd exponent. In both cases, as n increases, so as n gets larger, the exponents get larger, the graph flattens at the origin. So I want to show you what this means. And so if I have, let's do even exponents. So I know the even exponent, x squared, is a parabola. It looks like this. Well, what happens is if you do a power of 4, then it's going to come down, but it just becomes flatter. If you had a power of 6, it just comes flatter at the bottom. Almost looks like it's becoming wider. Okay, and so then what we can say about the odd exponents, our odd exponents here, like the x to the third, it crosses the origin and goes back up. Okay, so then if you have x to the fifth, still comes from negative infinity, but then it's going to just become more flatter at the origin. And then x to the fifth, we can see it becomes more extreme, flattens out, and then back up. Okay, almost looks like it becomes horizontal, even though it doesn't for both of these cases. That's what the exponent's going to do to your polynomial. Sketch the graphs of the following. All right, here we go. We're just going to do a couple points. We're going to do it by hand. And let's build a table of values. And what you can do is calculate. Let's go ahead and put in our origin, or 0 for x, not the origin, but 0. If you put 0 in, you're going to have 0 plus 2. 0 plus 2 is 2. 2 to the fourth, so my output is negative 16. Let's see if we put in negative 1. Negative 1 plus 2 is 1. 1 to the fourth is 1. Negative 1 is my output. I'm going to plot these already. 0, negative 16. I'm going by 2's. Negative 2. Negative 1, negative 1. Okay. If I put in negative 2, then I get negative 2 plus 2 is 0. 0 to the fourth is 0. There's my vertex. We can see this is opening down. It is shifted to the left. I can do my reflections. But what we're trying to see here is that this graph is a parabolic shape. And as it comes towards the vertex, it just becomes, it's flatter than what it normally is. And it's flatter because of the power of 4 as my degree. Okay. All right, let's go ahead now and let's look at my x to the third. Maybe what we can do here is let's use our translations, and then we can decide what values we're going to put in. This is 3 to the right and 4 up. Three to the right, 4 up. There's my initial point. That's usually at the origin. So let's put in 2 for an x, see what we get for an output. If you put 2 in, you get 2 minus 3, negative 1 to the fifth. Negative 1 plus 4 is 3. So over 2 up to 3. So if I put in 5, or I'm sorry, 4, 4 minus 3 is 1, 1 to the fifth is 1, 1 plus 4 is 5. And let's try putting in 0. Or 1, just to see what happens. 1 minus 3 is negative 2. Negative 2 to the fifth is negative 32 plus 4 is negative 28. We're not going to graph that point, but you can see that it comes then from a very low value. It's going to become flatter here and then back up. So that's what that graph would look like. In order for us to graph by hand, you can build a table of values. Plot your points, knowing what these curves and parabolas look like. You have to know what they look like in order to sketch them by hand. All right, we also have what's called the leading coefficient test. If f of x equals a sub n x to the nth, this is, again, just our standard little polynomial, then using the leading coefficient test to determine end behaviors. End behaviors is what the graph tends to do as x becomes very large, or as x becomes small. So what happens when x is large? Like goes to infinity. And what happens as x goes to, or comes small, or goes to negative infinity? That's what the end behaviors, that's what end means. All right, let's look at the test. Okay, so we've got 2 scenarios here. You got n is even, or when n is odd, versus if your leading coefficient is negative, or if you're positive here if your leading coefficient is negative. All right, this is what the graph would look like. If n is even and my leading coefficient is positive, then the end behavior, it's like a quadratic. It opens up. A power of 4 might look like this. Okay, 6. So there you have, you can see the end behavior both going from negative infinity to positive infinity. They are rising. Okay, so it rises to the left and right. Rises to the left and right. You can fill in this table. All right, negative. If A is negative, all that happens is it's reflected down. So they open down, and whatever the curves are, both sides are pointing down. Doesn't matter how many curves you have in here or how large they are. They open down. So in this case, falls to the left and right. Okay, that's when n is even. Your arrows will be going in the same direction, either both above or both going below. When n is odd, like the cubic, okay, or the fifth power, this is what your graph would look like. Okay. All right, when n is odd, this is what your behavior is going to look like. Let's start with when n is positive. So from left to right, it is going to be rising, but your end behaviors are, let's look at the cubic. So this is what the cubic would look like. So coming from negative infinity going to positive infinity. It's going up. It's slowly increasing. And then if I had a power of 5, you're going to see more curves, but still the end result. So you can describe this as it falls to the left. So that's what the left side of the graph does. And it rises to the right. Falls to the left, rises to the right. It'll always look like that as long as your leading coefficient's positive. Now when the leading coefficient's negative, it'll go the other way. Depending on how many curves you have, but this is where your arrows would be. Okay, so your arrows would be rises to the left, and falls to the right. All right, so those are considered to be they're called end behaviors because you're looking at what the ends of the graphs do. Where do the arrows go? Which direction do they go? All right, here's a few examples. What we're going to do is we're going to describe the end behavior, the right hand and the left hand behaviors. All right, we've got a power of 4. There's my degree, so it's even, and this is negative. Okay, maybe what you want to do is know that it does this, it opens down. Since it's even, the arrows are in the same direction, so to describe this, you would say falls to the left and right. Falls to the left and right. All right, here I've got part B, I've got an odd behavior, or an odd degree, and 5 is positive. So you have positive and it's odd. So I know it's gonna, look something like this. I just don't know where the numbers are at. This is gonna fall to the left, and it rises to the right. Falls to the left, rises to the right. That's how you can describe the end behaviors. It helps so that you know how to graph them on your own if you're sketching them by hand. Here's a few others for you to practice. You can see here, we'll just go through, I won't write them out, but we'll go through. If you want to pause the video and try them on your own and then start it back up and you can hear what happens. Here we've got a degree of 3, and this is negative. So this is going to tell us rises to the left, and falls to the right. Okay, I would want you to write that out. I'm just trying to abbreviate here for time. All right, even degree, and this is positive. So it's going to rise to the left and right. It's rising to the left and to the right. Here on the last one, my degree is 1, and it's negative. So it's going to rise to the left and fall to the right. Think of a linear equation with a negative slope, what the behavior is. All right, let's now look at the zeros of a polynomial function. The zeros state the following as being equivalent statements, where f is a polynomial function and a is a real number. All of these mean something about the polynomial. So here you've got, you might want to pause here and write this information down, but here you've got x equals a. That is a 0 of the function. A is a 0. Okay. X equals a is also called a solution, so we call them zeros and solutions. X minus a is a factor of the polynomial. So, such as this, we have sometimes our polynomial written in the form of x minus a and x, maybe a sub 1, and x plus a sub 2. So they can be in factored form. They're called factors. And finally, a0 would be the x-intercept. So all of those fit together as far as some things about the polynomial that are important. Repeated zeros. Sometimes when we have our polynomial functions, we've got zeros that occur at the same location. For a polynomial function, a factor of x minus a to the k power, where k is greater than 1, so maybe something like this, x minus 1 to the second, or x minus 2 to the third. This yields a repeated zero at x equals a. It's called the multiplicity of k. Multiplicity. Multiple zeros at the same number. See here on x minus 1 to the second, that means that there are 2 zeros of 1. X minus 2 to the third means there's 3 zeros at 2. So if k is odd, here's what happens with this type of description. If k is odd, the graph will cross the x-axis at a. I'll show you with these examples right here. So I'm going to look at the odd one. I've got x minus 2 to the third. So this is shifting to the right 2. This is what my graph normally looks like. 4 power of 3. It's a cubic. So what happens at that multiplicity, or at that zero, is it crosses at 2 and then it just keeps going. It crosses over the axis. If k is even, the graph touches the x-axis but does not cross over. So now let's look at the even polynomial that I gave you. This is shifted to the right 1. I know it's a parabola, but here's what happens. It comes from negative infinity, or rises to the left, and since it's an even, it'll intersect but then turn around and go the other way. So it acts more like a vertex. So this is what happens when they're even, and this is what happens when they're odd. So these are the odd ones, crosses over, and these are the even ones. They become vertices, like a maximum and minimum point. Let's look at these examples. Okay. All right, so I'm going to just quickly sketch these. I'm going to graph them. This is left 2, opens up, and I know that this it's a multiplicity of 2, so it just is going to cross and go back up, turn the other way. All the end behaviors can be noted here as well. Okay, this right here, I'm going to go 3 to the right, shifting 1, 2, 3 to the right. It opens up, or it comes from negative infinity to positive infinity. It would look like this. So it intersects and then crosses over and goes back up. Okay, x minus 6. So since 4 is even, I'm going to go left 6 here first. This is also opening up. But since my power is 4, not only is it becoming more flat at that number, but it'll hit the number at negative 6. Let's make this plus here, so we're talking about it being left. I shifted it the wrong way, but then it goes back to the other side, or it stays on that same side. Okay, so that's what happens with the powers here on your binomials. All right, example 3, find the x-intercepts of the graph. X-intercepts, where does this cross the x-axis? Well, when we've got 4 terms like this, our method would be, we have to go back to algebra 2, but our method is going to be factoring with 4 terms. We can factor 4 terms. What you would do is you group the first 2 together, group the second 2, factor what's like in the first section, x squared, and you get x minus 1 left. Factor what's like here in the second one, negative 1, and you get x minus 1. So your goal is to make sure that in the process of factoring that these are the same. Your expression would be x minus 1 and x squared minus 1. Well, with this one we can keep factoring. So we have x minus 1, x minus 1, x plus 1. I just factored the x squared minus 1, the difference of squares. So final answer, you've got 2x minus 1, so x minus 1 to the second, times x plus 1. So here's what I know. I've got x-intercepts at negative 1, 0, and I also have them at 1, 0, but since it's a power of 2 here, then that means it's a multiplicity. Okay, so there's 2 of these. All right, so there's the algebraic solution. Here's my graphical solution. I know it crosses here. I've got negative 1, 0 and 1, 0. So my graph is going to come up like this. I know my y-intercept is 1, so it's going to cross at 1, go back down to positive 1, but because it's an even, it makes a vertex and comes back up. Okay? So we have the multiplicity. At 1. This is just a reminder of your quadratic formula. Finds your x-intercepts, finds your solutions. All right, final example. What we want to do is find the x-intercepts of this graph. Well, here's how you find your x-intercepts. We've got a lot of methods, but you want to let your function equal 0 to start with. This is our algebraic method. You can see here I can divide everything by 5, so we've got 0 equals x squared minus 2x minus 1. We actually, this actually factors. So I'm going to look at, or you can see if it factors. If I have a minus here, it does not factor. So you use the quadratic formula. X equals negative b, so 2 plus minus square root of b squared 4 minus 4 times a is 1, and c is negative 1. All over 2 times a is 1. So we've got 2 plus minus the square root of 4 plus 4, which is 8, all over 2. This would reduce down 2 plus or minus 2 square roots of 2, all over 2. We can keep simplifying. It's going to be 1 plus or minus the root 2. 0. Those are our intercepts. Okay? All right. Graphing. So I know I've got x-intercepts at these two values, and they would end up being approximately 2.41. You just have to calculate it, and negative 0.41. So 2.41, right in about there, and negative 0.41. I know my vertex would be x equals negative b, so 10 over 2 times a, which is 5, so 10 divided by 10 is 1. If you put 1 back in, you would get an output of 5 minus 10 minus 5, which is equal to negative 10. So my vertex is 1, negative 10. And there you have it. So there's our graphical solution. You can see here we don't have any multiplicities because each of these intercepts were a power, just had one power to them. All right, there's your assignment for this section.